Now, change in entropy calculations. First one, change in entropy ds in heating a substance. Heating a substance. Now, initially, I'll take m grams of substance with specific heat C. Okay. So, amount of heat required to raise the temperature of m grams of substance through a small temperature rise. dt is mc dt, where C is specific heat of the substance. Okay. Entropy, change in entropy ds is equal to delta Q by T, we write. That is equal to mc dt by T. Okay. Now, total change in entropy, taking the substance from an initial temperature Ti to a final temperature Tf, will be integral, right, Ti to Tf mc dt by T. That is mc into integral 1 by T. Integral 1 by T dt is nothing but log T. Okay. Upper limit is final temperature Tf, lower limit is initial temperature Ti. So nothing but log Tf by Ti to the base E, right? Okay, so this is the change in entropy in heating a substance, mc ln, right? Tf by Ti, we write, natural log. Okay, Tf is final temperature. If final temperature is less than initial temperature, it means cooling the substance. Okay, log smaller quantity by bigger quantity, ds negative means the system's entropy is decreasing when you are cooling the substance. If final temperature is more than initial temperature, it is heating the substance. Okay, d log bigger quantity by smaller quantity will be positive. Okay, if you obtain positive value for ds, it means that it is increase in entropy. Okay. So, m is the amount of substance present, C is its specific heat, final temperature, initial temperature to natural log. Okay. Next one, we can extend this discussion to gases also. This is for, in general, true for either liquids or for solids. Okay, when I talk about gases we usually don't take mass into consideration, we take number of moles, n, into consideration. Then for gases we have seen there are two types of specific heats. One is CV, molar specific at constant volume, molar specific at constant pressure. Okay, so this is a second calculation, we can take this as second calculation. Okay, change in entropy. Okay, change in entropy of gases, heating or cooling, whatever it is. Okay, right, n moles of gas with a constant volume, suppose its temperature has been increased from Ti to Tf. Okay, what is the change in entropy? Right, ds is equal to instead of m grams we take n moles of substance. If the process is a constant volume process, okay, right, it is Cv isochoric, okay, molar specific at constant volume, ln Tf by Ti we can write. Okay, natural log to the base E, Tf by Ti. Okay, this is for change in entropy of n moles of gas, right? When it is changed, its temperature is changed from some initial value to final value. It can be cooling or heating, doesn't matter. Okay, because I'm using Cv here, the process should be a constant volume process. Okay, isochoric process it is. If it is an isobaric process, ds is equal to, right, ncp log, right, Tf by Ti. Okay, sometimes I'm using ln, sometimes I'm using log to the base E because both are same. Okay, so this is for a constant pressure process for gases. This is for constant volume process for gases. Okay, next one, change in entropy of a substance in a reversible isothermal process. Okay, in a reversible isothermal process, okay, suppose isothermal process means temperature will be maintained constant. You give some heat energy, its pressure may increase, volume may increase, anything may happen, but temperature should not change. So we have to calculate dq value or delta Q value. Okay, we have seen first law of thermodynamics is what? Delta Q equal to, right, du plus pdv. Okay, in a constant isothermal process, in a constant temperature process, for an ideal gas, internal energy remains constant because internal energy is a function of temperature only. If you maintain temperature constant, du will be equal to 0. So delta Q equal to pdv. Pdv is nothing but work done, delta W. So if you know the delta our work done, that is equivalent to the amount of heat. Okay, so delta Q equal to, what is delta W? Delta W, work done in an isothermal process. Okay, right, for a gas is nRT nRT log Vf by Vi, final volume by initial volume to the base E. Okay, n moles of gas at a constant temperature capital T. Its volume is changed from an initial value Vi to a final volume Vf. What is the amount of work done in that process? nRT log Vf by Vi. Okay, if Vf is greater than Vi, okay, log bigger quantity by smaller quantity, this will be positive. Work done by the gas, it is isothermal expansion. If Vf is less than Vi, it is isothermal compression. I have to do some work on the gas. Okay, nRT log smaller quantity by bigger quantity will be negative. dW negative means work is done on the gas. Okay, now what is change in entropy? ds equal to delta Q by T equal to this whole thing by T. So T and T gets cancelled. Simply nR, right, log Vf by Vi to the base E. Okay, this is the change in entropy in an isothermal process, isothermal expansion or compression. Change in entropy is calculated reversible isothermal expansion or compression. Okay, now we'll see what happens in an irreversible process. What is an example of an irreversible process, right? Free expansion, that is gas expanding against vacuum, against zero pressure means against vacuum, is called free expansion. Okay, it is like this. Okay, you take a what you call two chambers like this, okay, separated by a cock, right? Gas is on one side. Here volume is suppose say Vi. Okay, total volume of the gas, let us call it as final volume Vf. Okay, if I remove gas is at some initial pressure P, volume V, temperature T, volume Vi, temperature T. Okay, right, now the pressure here is 0 because it is vacuum. Now if I remove this stopcock, what will happen? Gas rushes into the second chamber and occupies the entire volume. What type of process it is? It is done under adiabatic conditions. Say I don't give any heat or take any heat. I don't give any heat or take any heat. Okay, so it is done under adiabatic conditions. Okay, gas is expanding against vacuum, means there's nothing to push here. Gas need not do any work here because PdV, pressure equal to 0, work done by the gas is 0, delta Q 0, delta W 0, delta Q is also 0 because I am not giving any heat or taking any heat. So internal energy du also, first law of thermodynamics. Okay, delta Q equal to, right, du plus delta W. Here, because gas is not pushing anybody to expand, it is expanding in against vacuum. So work done by the gas, PdV, P equal to 0, delta W equal to 0. I am not giving any heat or taking any heat. So delta Q equal to 0 implies what? Okay, internal energy du is also equal to 0. Okay, for an ideal gas, internal energy, change in internal energy is 0 means internal energy remains constant. When internal energy remains constant, temperature remains constant. Okay, but what type of process it is? An irreversible process. Okay, irreversible process, ds is greater than delta Q by T, we are seeing. Okay, now we can see what for a irreversible process, how do we calculate change in entropy? Means suppose a gas has gone irreversibly from some point A to a point B. Okay, it has gone some irreversibly like this. Entropy is a point or state function. Okay, here entropy is Si. Here entropy is SF. Say change in entropy ds is equal to SF minus Si. Okay, right, it depends only on the initial point and final point. Okay, right, now whatever the process may be, okay, it may be in any kind of irreversible process. Okay, but I'll find out an equivalent reversible process between these two. Means what is the equivalent reversible process for this irreversible process we see. Okay, then calculate the change in entropy for that reversible process. That will be the change in entropy for the irreversible process also, because initial entropy is same, final entropy is also remaining same. Okay, entropy is a point function or state function. It has gone irreversibly, but how do I calculate change in entropy for irreversible process? We cannot calculate change in entropy directly. Okay, there is no equality sign for irreversible process. So what do? I'll find out an equivalent reversible process. Okay, here what is that equivalent reversible process? Gas is expanding at constant what you call it temperature, because du equal to 0, temperature remains constant. Initial this volume is Vi say, finally this entire volume is Vf say. Means at constant temperature gas is expanding from Vi to Vf. I can treat this as a reversible isothermal process. Okay, so though this is an irreversible process, it is a free expansion. What is the equivalent reversible process? Since temperature is remaining constant, I can consider it as a reversible isothermal expansion and use the same formula. For free expansion also. So change in entropy in free expansion of a gas, right? Gas expands freely against vacuum from an initial volume Vi to a final volume Vf. What is the change in entropy, right? You can write it as ds is equal to, right, nr log Vf by Vi. nr log Vf by Vi to the base e. The expression is same. Okay, so the way of calculating changes in entropy for irreversible processes, find out an equivalent reversible process between the same 2 points. Calculate the change in entropy for that. You are getting the change in entropy for the irreversible process. Okay, right? Now, next one, change in entropy in phase change. There are changes called first order phase changes. There are change of phase from solid state to liquid phase, or liquid to what you call gaseous phase. Some changes are there, some changes are occurring in, okay, so phase changes are phase. One means system is going from one phase to another phase, solid phase to liquid phase to gaseous phase, like that. Okay, right? How to calculate, how many types of phase changes are there? There are basically 2 types of phase changes, first order phase changes and second order phase changes. In second order, again, there is a special case called lambda transition. Okay, that we will see after this Maxwell's equations. Now we will talk about first order phase changes only. Okay, what are first order phase changes? Right, melting of a solid, boiling of a liquid. Okay, in first order phase changes, system absorbs some heat for the phase change to occur. Okay, the delta Q is known as latent heat. Okay, latent heat. Okay, commonly denoted by capital L. Okay, now you take, for example, ice at minus 10 degrees Celsius. Ice at minus 10 degrees Celsius you take and start heating it. Okay, when you start heating it, right, the ice keeps on getting heat energy, its temperature keeps on increasing. Up to what point temperature keeps on increasing? From minus 10 it becomes minus 6, minus 4, minus 2, minus 1, 0. Once ice comes to 0 degrees Celsius, right, you continue heating it, but its temperature will not increase. Its temperature will not increase for 5 minutes or 10 minutes. Okay, depending on the way you are heating, temperature remains. Initially, when you started heating it from minus 10 degrees Celsius, its temperature went on increasing from minus 10 to 0. But 0 degrees Celsius, its temperature will not increase, but you are heating it. What is happening to the heat energy you are giving? Right, that heat energy is used inherently to convert this ice into, right, water. To convert ice into water. Okay, till the last bit of piece of ice, right, transforms into water, its temperature will not increase. Okay, because it is not showing up itself, that heat is not showing up itself as rise in temperature, we will call it as hidden heat or latent heat and denote it by L. Okay, right. Now, up to what point? Till the last bit of ice also transforms into water, temperature will not increase. Now, what happens, right? Entire substance got converted into, right, water. We will get water at 0 degrees Celsius only. Okay, so at constant temperature of 0 degrees Celsius or some temperature T1, okay, system is absorbing heat. That heat is not used to raise the temperature, but to change the phase of the substance from solid phase to liquid phase. Now, if you start heating the water continuously again, from 0 degrees Celsius, temperature of water keeps on increasing. It becomes 25 degrees, 50, 75, 99, okay. Up to 100 degrees Celsius, temperature keeps on increasing continuously. Temperature keeps on increasing continuously, right? Water now will be at 100 degrees Celsius. You continue heating it. Okay, when it reaches that 100 degrees Celsius, okay, even though you continue to heat, its temperature will not increase. Okay, then what is happening to all the heat you are giving to the substance means water's temperature remains as 100 degrees Celsius, but all the heat you are giving will be used up in converting water into water vapor or steam. Okay, like this, it becomes steam and keeps on going out. Okay, if you hold this steam completely till the last drop of water becomes steam, right, temperature of water will not increase. It will remain as 100 degrees Celsius only. Okay, that is known as what you call, this is initially known as latent heat of fusion we call. Okay, because for solid to liquid transition, from liquid to gaseous transition, vapor transition, it is known as latent heat of vaporization. Okay, for 1 gram of ice at 0 degrees Celsius to convert into 1 gram of water at 0 degrees Celsius, okay, there is no temperature change, only phase change is involved. That latent heat of fusion we call it as 80 calories per gram. 80 calorie per gram. Okay, this is known as latent heat of fusion of ice. Okay, similarly here at 100 degrees Celsius, till entire what you call, till last drop of water transforms into steam, temperature will not increase. Okay, that's called latent heat of vaporization. I'll call it as L2. I'll call this as L1 for our example. Okay, right, this is about 540 calorie per gram. Okay, 540 calories per gram. Okay, this is latent heat of vaporization of water. That's why, see, water at 100 degrees Celsius, steam at 100 degrees Celsius. Okay, which is more dangerous to us? Okay, when you are exposed to water at 100 degrees Celsius, you will get damaged in one way. Okay, when you get exposed to steam at 100 degrees Celsius, the damage will be more. Why? Because for water at 100 degrees Celsius, unless you give 540 calories per gram, it won't become steam. Means the amount of heat content in steam, though it is also at 100 degrees Celsius, is more than that in water. Okay, that's why steam harms you much more than what water at that temperature does. Okay, right, once the last drop of water also transforms into steam, now you continue heating, temperature of the steam will keep on increasing. From 100 it becomes 105, 110, 115, like that. 150 like that. Of course, our standard temperature and pressures I am talking. Okay, standard pressure. Okay, right, 540 calories per gram. Okay, is the latent heat of vaporization of water. This is latent heat of fusion of ice is 80 calories per gram. I'll call this as L1, I'll call this as L2. This is the amount of heat taken, delta Q. And now we can see from entropy point of view, disorder point of view also, in ice state, the molecules are all fixed to their respective positions. Disorder is less. All that water molecules can do is what? Simply vibrate about their equilibrium position. That's all. Okay. Whereas, if I transform that ice into water, okay, water molecules can move freely throughout the volume of the water. Means what? Disorder of molecules is increasing. Okay. Entropy also should increase. Okay. Right. So, what is that change in entropy? Right. ds equal to delta Q by T. ds equal to delta Q by T. In the case of solids becoming liquids, delta Q is nothing but latent heat, right? For 1 gram, it is L1. So for m grams, it is m L1 by, I'll call it as T1. T1 is that constant temperature at which all these processes are isothermal, isobaric processes. Okay, they occur at constant temperature and they occur at constant pressure also. Till entire ice transforms into water, temperature will not change, pressure also will not change. Okay, till entire water, last bit of water drop also transforms into steam, temperature will not increase, pressure should not be changed. Once you change pressure, melting point will keep on changing. That is another aspect known as Clausius-Clapeyron's latent heat equation. That we will see how melting point and freezing points are affected by pressure. Okay, right? So this is what you call one expression, mL by T, general expression. If you are talking about latent heat of fusion, means solids becoming liquids, right? mL1 by T1 I'll write. Liquids becoming gases, okay, or what you call vapors, we'll call it as mL2 by T2, right? ds, change in entropy, is this expression, general expression for change in entropy during a first order phase change is mL by T, okay, where L is latent heat, okay, that is heat required for the phase change to occur per gram. If m grams of substance is taken, it is m into L. The temperature at which that phase change occurs is capital T. This ds is equal to mL by T, we write. Okay, now you take a transition like this. I'll start with what is known as ice at minus 10 degrees Celsius. So initially I'll take some sample ice at minus 10 degrees Celsius. Okay, I want to convert that into steam at 110 degrees Celsius. Okay, so taking m grams of ice at minus 10 degrees Celsius, I want to transform it into steam at what you call 110 degrees Celsius. steam at 110 degrees Celsius. What is the total change in entropy in this phase changes, in this vertical transformation? Now, how many processes are involved, you see? First of all, we have to heat ice from minus 10 degrees Celsius to 0 degrees Celsius. That is, heating a substance is there. Okay, to 0 degrees Celsius, ice only will get. Okay, ice at 0 degrees Celsius should be first converted to water at 0 degrees Celsius. Means this is a phase change. This is water at 0 degrees Celsius. This is phase change, first order phase change. Now water at 0 degrees Celsius should be heated to water at 100 degrees Celsius. Okay, water at 100 degrees Celsius. Okay, this is again heating a substance. Okay, now water at 0 degrees Celsius should be converted to steam at 0 degrees Celsius. Okay, sorry, steam at 100 degrees Celsius means it is like this. Okay, it will be like this. So water at 0 degrees Celsius should be heated to water at 100 degrees Celsius. This is heating. This is a phase change. Okay, this is a heating process. This is also heating process. Okay, ice at minus 10 to ice at 0, heating process. Okay, ice at 0 degrees Celsius should be converted to water at 0 degrees Celsius. It is phase change. Okay, now water at 0 degrees Celsius should be heated to water at 100 degrees Celsius. This is also again heating process. Now water at 100 degrees Celsius should be converted to water at steam at 100 degrees Celsius. Steam at 100 degrees Celsius. This is again a phase change. Okay, now steam at 100 degrees Celsius should be heated to steam at 110 degrees Celsius. Steam at 110 degrees Celsius. This is again heating. So how many steps are involved here? 3 heating processes and 2 phase changes. One is solid to liquid phase change and liquid to gaseous phase change. So change in entropy in heating the substance, I'll take it as DS1. Change in entropy in this phase change, I'll take it as DS2. Change in entropy in heating the substance, I'll take it as a DS3. Change in entropy in this phase change, I'll take it as a DS4. Change in entropy of this heating, I'll take it as DS5. So what is total change in entropy? Total change in entropy in taking ice at minus 10 degrees Celsius to steam at 110 degrees Celsius. ds equal to ds1 plus ds2 plus ds3 plus ds4 plus ds5. Okay, now what is ds1? ds1 equal to heating the ice from minus 10 degrees Celsius to 0 degrees Celsius. Okay, that is nothing but we have seen m grams of ice with specific heat of ice C1. Okay, right, log, right, final temperature by initial temperature. Final temperature is 0 degrees Celsius. 0 degrees Celsius means it is 273 Kelvin. Okay, so final temperature is 273. Initial temperature is minus 10 degrees Celsius means 273 minus 10, 263 degrees Celsius. Here, this is MC1 log 273 by 263. Now, what is DS2? Right, changing ice at 0 degrees Celsius to water at 0 degrees Celsius. It is nothing but first order phase change. M grams of ice you have taken. Latent heat of fusion, I'll take it as L1. It is occurring at a temperature T1. Okay, what is the temperature T1? 0 degrees Celsius means M L1 by 0 degrees Celsius means 273 Kelvin. This is DS2. What is DS3? Now, this water should get heated from 0 degrees Celsius to 100 degrees Celsius. That is, DS3 is equal to, right, M. Now, see, specific heat for ice is different, for specific heat for water is different, specific heat for steam is different. Okay, I'll take specific heat of water as C2, right, log from which temperature to which temperature, from 0 degrees Celsius to 100 degrees Celsius. 100 degrees Celsius means 373 Kelvin by 0 degrees Celsius means 273 Kelvin to the base E. Okay, right, the next phase change is water. Now we have water at 100 degrees Celsius. This should be heated to what you call steam at 100 degrees Celsius, first order phase change. So DS4 is equal to, first order phase change means M, right, M grams of substance. Latent heat of vaporization, I'll call it as T2 by, right, the temperature at which that phase change is occurring. Water is becoming steam, 100 degrees Celsius. 100 degrees Celsius means, right, it is 373 Kelvin. Okay, last one, DS5. Okay, dsy. Now steam at 100 degrees Celsius should be heated to steam at 110 degrees Celsius. ds5 equal to right, m, what specific heat of steam, I'll take it as C3. Okay, log to which temperature? 110 degrees Celsius. 110 degrees Celsius means 273 plus 110. It is 383 by, initially it is at 100 degrees Celsius, that is, it is at 373. Okay, right? These are the 5 different expressions for changes in entropy. So the total change in entropy for this entire transformation is nothing but summation of all these things. Okay, you add up ds1 plus ds2, etc., etc. You will get the change in entropy. Okay, right? This is another process. Next one. Okay. Now, change in entropy in heat transfer. Okay, heat always flows from high temperature to low temperature, we have seen. Okay, why heat should flow only from high temperature to low temperature? Why it cannot flow back? Means we have seen it is an irreversible process. Okay, in an irreversible process, entropy of the universe should always increase. So, all natural processes in the universe will proceed in such a way such that the entropy of the universe increases. That is the second law of statement. In terms of entropy, Clausius has given that statement. Okay, now you consider a substance here. Change in entropy in heat transfer. You consider a substance which is at a temperature T. Okay, right? There is another substance B here. I'll take this as A, I'll take this as B. This is at a lower temperature T2 such that T1 is greater than T2. Okay, when you join these two objects, heat flows from high temperature to low temperature. We are seeing why it is happening like that. Why cannot it flow backwards on its own? Means on its own heat has to flow, means it becomes like a refrigerator. You have to do some external work. Okay, right? Heat flows like this. Say delta Q amount of heat has flown from A temperature to, A to B. Okay, now what is this one's, and because heat is flowing out of the substance, right, this one's temperature decreases. What is the change in entropy of this one? Right, delta Q by T1, I write. Delta Q by T1. Okay, because it is decrease in entropy, I'll put minus sign here. Now, the same delta Q amount of heat is going into B, right, which is at temperature T2. Okay, so what happens to its entropy? Because heat is getting added, its entropy will increase. Okay, change in entropy of B, ds2 is equal to same delta Q by T2, I'll write. It's change in entropy. Okay, what is the total change in entropy of the entire system plus surroundings plus universe? Okay, whatever it is, ds is equal to, right, ds1 plus ds2. That is equal to, okay, delta Q by T2 minus delta Q by T1. Delta Q by T1. Is this positive or negative? Just guess. Okay, is it positive or negative? Okay, right, delta Q is same, means numerator is same in both the terms. Okay, T2 is here, T1 is here. T1 is greater than T2, I told. So delta Q by T2 will be a bigger quantity than delta Q by T1. Means bigger quantity minus smaller quantity, right? ds is positive only, means entropy of the universe is increasing in this process. Entropy of the universe is increasing in this process. By chance, if heat flows from lower temperature to high temperature on its own, say, okay, right, then what will happen? This one's entropy decreases, this one's entropy increases. Means I have to put what you call minus sign for this and what you call positive sign for this. Okay, so as the ds is equal to delta Q by T1, delta Q by T1 minus delta Q by T2 it would be. Delta Q, T2 is smaller than T1, no. So delta Q by T2 will be higher, bigger one. Delta Q by T1 will be lesser one. So entropy of the universe, ds will be negative, means entropy of the universe is decreasing. In no process, entropy of the universe can decrease. See, entropy of the universe can either remain constant or it should increase. That's all. It remains constant if the process is a reversible process. It always increases if the process is an irreversible process. Okay. Right, that's why heat always flows from high temperature to low temperature. Natural phenomena, why they occur in the way they are occurring, okay, we can understand from this entropy principle. Okay, why time keeps on flowing in one direction only. Okay, we cannot reverse time. Why? It's against what you call second law of this thing. If I drop my chalk piece, it breaks into 4 pieces. I can understand from entropy point of view only. When the chalk piece is intact, okay, disorder is less, right? Entropy is less. When it falls down, breaks into 4 pieces, disorder is increasing, entropy is increasing, entropy of the universe is increasing, okay, right? So chalk piece should always, where chalk piece should fall down, it always breaks into 4 pieces. Never 4 pieces stick together and come to your hand. In that case, if that happens, what will happen? One interesting phenomenon is, see, the nature universe is in all natural process in the universe. See, sun is giving us radiation. Is it reversible or irreversible? It is an irreversible process. We cannot send what you call the radiation back into sun. Impossible. Okay, similar radioactivity, alpha, beta, gamma particles are coming out. It's all irreversible process. I can never push back alpha particle into that nucleus again. Whatever I do, I cannot send that alpha particle into the nucleus again. I cannot send the beta particle into the nucleus again. These are all irreversible processes only. Once they come out, they cannot be reversed. So all natural processes occurring in the universe are always irreversible process. In an irreversible process, entropy of the universe keeps on increasing. Entropy is increasing means disorder of the universe is also increasing. So the ultimate purpose of the universe is in which way universe is proceeding. Universe is not proceeding towards order. Universe is proceeding towards total disorder. Okay, because entropy, all processes are irreversible only. So entropy of the universe keeps on increasing. Okay, there is no conservation law for entropy. Entropy has no conservation. Okay, entropy keeps on increasing. So entropy is increasing continuously means disorder is increasing towards maximum. So we say entropy running down of the universe we call. Okay, universe is running towards total disorder or chaos. Ultimate chaos will occur. Okay, the purpose, the aim of the universe is not running towards order. Aim of the universe is running towards total disorder. Okay, so going towards this disorder is the natural tendency of the universe according to second law of thermodynamics. Okay, from that way we can understand which natural processes are possible in nature, which natural processes are not possible in nature. Anything where entropy decreases or remains constant is impossible in nature. Entropy has to increase only. In that way only process will happen. Why heat engine must reject some heat into the sink at lower temperature? Okay, what is Kelvin Planck statement says that without rejecting any heat, no heat engine can transfer heat from high source and extract heat from a hot source and completely convert it into work. Impossible, it said. Why? Now you see, you are taking heat from a source at higher temperature. Okay, right? You are taking Q1 amount of heat. A heat engine, suppose it converts everything into work. All heat is converted into work. What will happen? Right? Here the work done. There is no heat involved here. So no change in entropy. System goes back to its initial point. So system's entropy remains constant. Okay. It is doing work only. It is not giving any heat. Means here there is no delta Q, no delta T here. Okay. But what is happening to the temperature of the, entropy of the universe or entropy of the source? Okay. It is decreasing by, because you are taking out Q1 amount of heat. Entropy decreases by what amount? Q1 by T1. Okay, right? Source entropy is decreasing. System's entropy is remaining constant means universe entropy is decreasing. Universe entropy is decreasing, which is impossible. Means in order to maintain that constant, entropy increase, okay, tendency of nature, there should be one sink at lower temperature. Heat engine must reject some heat Q2 into the sink such that increase in entropy of the sink will be Q2 by T2. If you do it in a reversible manner, right, Q1 by T1 will be equal to Q2 by T2. If you do it in an irreversible manner, Q1 by T1 will be less than Q2 by T2. Entropy increases. Entropy of the universe increases. Okay. Means, right, in order to have the entropy of the universe to increase or to remain constant, right, you must reject some heat into the sink at lower temperature. There is no other option. So, right, if you convert all heat into work, right, efficiency eta will be equal to 1. So, according to second law of thermodynamics, eta cannot be equal to 1. Okay, right, ideal heat engine, though Carnot engine is an ideal engine. Okay, even its efficiency is less than 1 always. Okay, why we must have some Q2 to be rejected into the sink? Now I can understand from entropy point of view. Unless some heat goes into a sink at lower temperature, entropy of the universe is not increasing. Okay, right? Entropy of the universe will decrease, which is impossible. Okay, so such a heat engine is impossible. We need to have 2 different temperatures, one higher and one lower temperature for any heat engine. For a refrigerator also, heat should be transferred from low temperature to high temperature means we have seen entropy of the universe decreases if it happens. So I have to do some amount of work on it. When I do some amount of work, this Q1 by T1 will be equal to Q2 by T2, right? Then Q2 by T2 will be equal to Q1 by T1 here. Then what will happen? Entropy of the universe increases. If it's an irreversible process, irreversible refrigerator. If it is a reversible refrigerator, entropy remains constant. Okay. Now we can understand all natural things, why they are happening in the way they are happening. From entropy point of view, we can answer everything. Okay, you bring one hot tea in a cup and put it here. Within 5 minutes, right, it cools down. Okay, in that way, heat is going from high temperature to low temperature surroundings. If heat comes from surroundings and tea becomes hot, means what is happening? Heat is flowing from low temperature to high temperature, which is impossible. Okay. Similarly, you drop something falls down and breaks into 4 pieces. In that way only entropy of the universe increases. Okay. Disorder is increasing. If 4 pieces join together and come into your hand, okay, entropy of the universe decreases, which is impossible. Okay, like this we can understand everything. Okay, all natural phenomena can be understood from that one concept called entropy, which was introduced by a scientist called Clausius. Okay, one of the most important terms in physics, we say. Okay, second law of thermodynamics and concept of entropy. Okay, right, now the question is, you be of any religion. Okay, all religions, irrespective of their place of origin, whatever it is, okay, they say that every religion says that you should be more orderly in nature. Okay, you should get up at morning 4 o'clock, you should be very systematic in life. Okay, you should do this thing, you should not do that thing, etc., etc. You have to lead a perfectly ordered way of life. Okay, is it not against second law of thermodynamics in terms of entropy? It's my doubt. Is it not against? Are we not going against the nature of the universe? Universe is going towards disorder. So increase in disorder is the nature of the universe. Okay, but what do all religions are saying? Okay, any religion for that matter, no religion asks to be in a disorderly manner. Every religion expects you to be living your life in a very systematic manner only. Means you have to increase your order. That's what religions say. Okay, of course there are 1 or 2 religions. In India we used to have some Charvaka philosophy where they don't believe anything. Okay, there is no religion for them. All that their job is to what? Simply eat, drink, and make fun and enjoy. That's all. Okay, don't bother about afterlife. There is nothing. This is the only life given to us. So live happily, enjoy as much as you can, and die off. That's what is there. That, of course, that system did not survive for a long time. People have rejected that theory. Similarly, in European countries also, there were some people known as Epicureans. Who are Epicureans? Who have to simply drink, eat, and make merry. That's all. Okay, they don't bother about any religion or any systematic order, whatever it is. Whatever comes to your mind, you do and live happily. That's all. Don't bother about consequences, because there is nothing. That's called Epicurean way of life. Even that system also did not survive, even in Europe also. Okay, right? Means those religions or concepts which are proposing disorder are not sustaining on this earth. Okay, those religions which are preaching perfect order in life only are surviving. Let it be Hinduism or Jainism or Sikhism or Buddhism or Islam or Christianity, whatever it is, Kabbalah, and whatever it is. Okay, everybody wants you to live a systematic life. Okay, but what is second law of thermodynamics saying? Be as disorderly as possible, then only you are close to the nature. In that way, are we not going away from nature's principle of going towards total disorder? Just guess. Okay, of course, I have my own answer. I want you also to ponder upon this. Okay, and give me your comments in the form of feedback in the form of comments. Okay, when time comes, I'll explain this also. Right? Why religions preach order? That also we can see. It is also according to thermodynamics only. Okay, law of thermodynamics. Everything we can understand, right, from one principle called entropy. Okay, right? So on this happy note, I'll take leave for today. We'll continue in the next video. Thank you.